All right, well, we're very excited to have Melissa here in person to tell us about her cool work on dark matter blobs. So take it away.
And I can take my mask off?
Yes.
Okay. Hello, this is good, I'm not very loud. So hi, I think I've met everybody here at this point. I'm Melissa Diamond. I'm an imminently graduating grad student at Johns Hopkins. And I'm going to be talking to you about some work I'm finishing up with David E. Kaplan and Surjit Rajendran. And it's about dark matter blobs, how they form binaries and they merge, and how we can use that to probe parts of dark matter parameter space, which are otherwise very difficult to reach. All right, so I'm just going to do some basic introduction and sort of give you a sense of why I'm interested in this part of dark matter parameter space. So as I'm sure many of you know, dark matter has been a central quandary of cosmology, astrophysics, and particle physics at this point for decades. And despite our best efforts, we have a limited understanding of what dark matter is, a limited number of positive things we can say about it. So we know it composes something like 26% of the mass energy in the universe, while ordinary matter, standard model stuff that we're familiar with, really is only about 5%. So 80% of the gravitating matter in the universe is dark. By dark, I mean that it interacts with us through gravity, but not through any electromagnetic interactions, at least none that we've been able to observe to date. And this dark something, which is filling the universe, plays a very important role in shaping it into the one we know and love today. Dark matter is providing the gravitational scaffolding, which is holding galaxies and clusters of galaxies together, but it also provided the seeds, which allowed those galaxies to come together in the first place. Now, because this has been such an important thing to try to understand for, at this point, decades, there are a wide range of different ideas about what dark matter might be. So I'm showing you here a landscape of dark matter candidates, and this covers maybe 70 or 80 orders of magnitude in mass. And we like to group different dark matter candidates together by their masses, because things with similar masses often behave in similar ways, or we can rely on similar techniques to try to observe them. So starting with the lightest dark matter, down here we've got ultralight dark matter, where the favorite candidate right now is axions, axion-like particles. This is very much an active area of research right now. I'm going to use the word direct detector somewhat loosely, but there's an array of different direct detectors set up to try to observe these objects, but we can also use different types of astrophysical searches, looking at how do axions interact with black holes, how do they interact with magnetic fields around neutron stars. We even have cosmological tools because axions are thought to cause polarized light to rotate. And so we can look for this effect in the cosmic microwave background. So this is very much an active area of research. A lot of energy and thought is being put into here right now. Moving up to higher masses, we've got particle dark matter. So this is dark matter that behaves as particles, sort of similar masses to ordinary standard model particles. For a long time, specifically WIMPs, weakly interacting massive particles, were the favorite dark matter candidate. And so there's a very well-established research program around dark matter in this mass range. Again, a variety of different direct detectors, but we can also use colliders because these are high energy collisions. One could reasonably produce dark matter if it's in this mass range at colliders. So there have been searches at the Large Hadron Collider, for example. And again, we have astrophysical effects that we can rely on. So dark matter interacting with itself, producing gamma rays, interacting in the sun, producing neutrinos. A lot of options here too, because this has been something we've been interested in for a long time. And then moving up to the highest masses, we've got primordial black holes and MACHOs, massive compact halo objects. So primordial black holes, similar to astrophysical black holes, except They've been around since the beginning of the universe, and they can exist in a much wider mass range than astrophysical black holes typically do. This is parameter space that we actually have a lot of different tools to work with and has been very well constrained. This type of dark matter is really much too heavy for us to use any sort of Earth-based direct detectors to try to look for them. There just aren't enough passing through the Earth that would be reasonable. Our best tool is gravitational lensing, where one of these heavy objects could pass between us and a bright source behind it. Then the light from that source will be bent or distorted in some way by the heavy gravitational object, and that's a signal that we can look for. This has largely constrained a lot of this parameter space. We can also look at wide stellar binaries. These are unstable binaries which would be disrupted by a passing black hole. We can look for excess radiation from these black holes eating, and we can look for gravitational wave signals. So lots of tools, pretty constrained at this point. Now you may have noticed that there is a big gap in my dark matter landscape here, which I've been neglecting. And the reason I've sort of ignored this chunk of the plot is because this is a much more neglected part of dark matter parameter space. Now, of course, you could argue that maybe we've been ignoring it because there's nothing worth looking for in here. There's really no reason to set up an experiment if you don't know what you're trying to find. But I would argue there are actually a wide variety of dark matter candidates in that mass gap there. The first general class of them is what I'm going to call stable black holes. Generally speaking, black holes aren't great dark matter candidates in this mass range because they're so light that they Hawking radiate and they lose too much of their mass or they produce too much radiation. However, there are ways around this. The easiest is to just look at primordial black holes in the 10 to the 17 to 10 to the 21 gram mass range. This is not particularly well constrained parameter space, and these are black holes which are heavy enough that they don't Hawking radiate too much, but light enough that they're quite difficult to get at with our current lensing experiments. But you could also look at extremal black holes, which carry some kind of charge, ideally a dark charge, which protects them from decaying further. There are some higher dimensional black holes, which might not decay in the same way as ordinary ones do. And of course, I've seen some papers about black hole relics. So little Planck mass relics left behind from a black hole that decays. There are some papers suggesting those could be dark matter also. Moving on, we have what I'm going to call nuclear dark matter. You might heard of this referred to as a nugget or a blob, but here blobs are any dark matter in this mass range. Nuclear dark matter is composed of some sort of small constituent particles which have a strong self-interaction, similar to what we see in the standard model perhaps, that allow them to form dense nuclei-like structures, but either with an additional interaction, which allows these structures to become quite large and remain stable, or without some of the interactions we have in the standard model, which destabilize nuclei as they get too large. And then finally, we have exotic compact objects. So this includes things like boson stars, which are typically made of ultralight dark matter, sort of like a astrophysical scale Bose-Einstein condensate, and dark fermion stars. These would resemble neutron stars. So if you have a cloud of dark matter made of fermions, it could collapse and then be supported by degeneracy pressure. Now, this is not an extensive list or a complete list of all the different types of dark matter in this mass range, but it's just to give the sense that there are a variety of different things worth looking for in this part of parameter space. Which then begs the question, why aren't we really looking? And ultimately, it's very hard. Blobs are really too heavy to show up in any collider. There aren't enough of them that we could expect many to pass through the Earth for a direct detector signal. And they are still too light for at least microlensing to be an effective way to look for them. And so without a lot of the tools we normally rely on, we're forced to either look for astrophysical interactions or blobs interactions with themselves, which is what brings me to the topic of my research, blob binaries, which are going to come in and save the day and give us a way to look at this sort of dark matter. Now, if you're familiar with binaries of primordial black holes, then this will be very familiar to you. I'm basically taking the analysis that's been done for primordial black hole binaries and applying it to blobs. But if you aren't familiar with that, the basic idea is that
Just to make sure that blobs, by blobs, you mean things like there's some strong interaction in the dark sector that they form compact objects or.
yes. Yes, so dark matter in this heavy, sort of too heavy to see with detectors, too light for gravitational lensing mass range, that is reasonably compact.
Why do they form blobs from early universe?
Why do they form those compact structures in
Yeah.
the first place? I mean, that's going to depend on your specific blob model, but a strong self-interaction would be a reasonable assumption.
Like dark BBN.
Maybe the question is
Dark
like,
BBN?
Yeah.
Okay.
yeah, how likely like two blobs meet each other and form some binary states you're interested
Well, I will get to that in a minute. Yeah, so but the basic idea is that blobs early in the universe, and by early I mean temperatures of about an MeV down to maybe 100 eV, will form these little gravitationally bound structures. Over time, they radiate gravitational radiation and eventually merge. What's exciting about this is that, oh, this thing's got a fun delay. Okay, what's exciting is that this happens a lot. This is a fairly high merger rate, happening more than random collisions of these objects in the Milky Way. And it's reasonably model independent. And these mergers can produce some sort of observable signal, be it gravitational or electromagnetic. The details will depend on the model, but there are still lots of these events happening. Now, this green region here, this is the mass range where a dense blob of dark matter, whatever it may be, could reasonably form a binary, and those binaries could be merging at a high rate in the universe today.
You probably said this already. How many binaries do we expect?
So a small fraction of the blobs are merging, but I'll give you an actual number in a few slides. So the basic mechanics here are that we go back into the early universe. And at this time, we assume that the blobs are cold. They're much more tightly packed together than they are now. And they're slowly getting pulled apart with the Hubble flow. We can describe their separation with roughly a Poisson distribution. But if there is a pair of blobs which happen to be particularly close to each other, then they can form a binary. So the details of the binary depend on the initial separation between the blobs, that's x, the co-moving distance, and the mass of the blobs. They're attracted to each other through gravity, but also being pulled apart by Hubble expansion. So the binary actually forms roughly when their infall time equals a Hubble time, or the time it would take the universe to expand by an order 1 factor. So the redshift when they decouple is going to depend on the blob mass, with heavier blobs forming binaries at earlier times and lighter ones forming them later, and also their initial separation. Blobs which start out closer together can form binaries at earlier times. This is what gives us the binary semimajor axis, which is just how large their orbits are. Binaries which start out, blobs which are further apart will form bigger binaries, and heavier blobs will tend to form smaller ones just because the binary itself forms at an earlier time. And so there's less, they get pulled apart less by Hubble expansion. Now, if blobs, yeah?
That's good. We observe some binary system, say formed by asteroids, like around this mass, 10 to 24 gram. We see already see some binary formed by asteroids, like on moon, like this light.
Oh, you're saying that already exists?
Yeah, is that, or do we observe or?
Oh, I wouldn't say we've observed, I mean, astrophysical binaries perhaps would exist, but I wouldn't say we've observed like dark matter binaries of this sort yet. I'm sort of describing an effect that with a specific model, one could actually look for.
Yeah, but maybe my question just for the astronomical binaries, for that around that mass, do we have any observation on those things?
I guess not to my knowledge, but I also would say that, you know, gravitational wave detectors aren't set up to look for them because these are much lighter masses than what they're designed for. And I don't know that there's other observable effects. I don't know that you get a bright signal from, say, a moon colliding with another moon. I wouldn't expect we could see that.
But like by similar theory, like estimation that should happen.
Well, the difference I would say is that at least the blobs that produce interesting signals are certainly much more dense than like the moon, for example. There are a lot more mergers happening. And I mean, there's a variety of masses, so there are a variety of different types of signals. But I would generally say you're banking on there being some sort of electromagnetic signal produced in the interaction. Yeah, oh, actually also the other thing is these are much harder collisions than what I would expect between like two moons. Because they're generally moving at fairly relativistic speeds when they collide. Good. Okay, cool.
Sorry,
Yeah.
Can I ask one question?
Yeah.
So once this blob form at redshift of Z sub B,
Mhm.
should I think of the A being a fixed value independent of the redshift, like afterward?
So this is dictated by the redshift when the binary initially forms.
Right.
So this x to the third over m is sort of getting folded into this expression here.
Right. And then it stays the same value then during the evolution, or it changes.
I mean, the size of the binary is going to change over time as it loses energy. It's slowly shrinking, but it'll spend most of its life at roughly this size, I would say.
I see. That was, okay.
Yeah, so, but if these blobs are the only things in the universe, then we would just have a head-on collision. Instead, there are lots of other blobs floating around, and the ones in our binary are gravitationally attracted to all of these other blobs. And there are tidal forces between the ones in our binary and the other blobs, and this perturbs them somewhat as they're infalling, and is what gives us an eccentric binary and not a head-on collision. The eccentricity describes how circular an orbit is. It's 0 if it's perfectly circular. It's 1 for a head-on collision. So we can estimate this based on the distance between the binary and the next nearest blob. That's the one that torques it the most strongly. So now that our binary is formed, it has to now spin down for a merger to happen. How quickly this takes place depends on how heavy the binary is. With heavier blobs emitting more gravitational radiation, so they merge more quickly. How large the binary is, where larger binaries are going to take more time for the blobs to fall in toward each other. And it's actually quite sensitive to the starting eccentricity, where the closer this is to 1, the more eccentric the binary is, the more quickly the merger happens. For mergers happening today and at other early times, the merger rate is very dominated by the most eccentric binaries. And this is sort of an important detail in some of the dynamics for actually doing the estimate. So then we actually get the blobs merging. Ultimately, we can estimate a merger rate by looking at an initial spatial distribution of blobs and using that to estimate a distribution of binary parameters, which gives us a distribution of merger times. And effectively, the fraction of blobs merging today, or the fraction of binaries merging today, really just comes from the fraction of blobs which had the correct initial separations to form a binary that would merge today. So for a sense of scale, if I have a 10 to the 15 gram blob, then there are about 90,000 mergers happening in the Milky Way halo per second if that blob was all of the dark matter. So F here is the dark matter fraction, mass is here. And this weird fraction is really about mass to the -1. So there's a
So how
lot,
do you estimate, so given a like distribution of blob at a given time,
yeah,
and then you look at you have a distribution of x, right, as an initial condition, say.
yes,
And then for a particular axis, then if Hubble is equal to infinite time, those can form binaries, right? So then you just look at the random distribution of the x, and then you estimate the number of mergers.
yes. So there's a random distribution of X and also Y, the distance to the next, like this third blob, which is the next nearest
Eccentricity.
one.
Okay.
And from that, you get a collection of binaries, and they're merging at all different times.
Uh-huh.
So then it's just which of those binaries have the right parameters that they'd be merging at any given time.
Okay, so then roughly speaking, what is the fraction of a blob that actually goes through the merger formation? Is there any sense?
I think ultimately it could be even like an order one
Oh, I see.
fraction. A lot of them form binaries. A lot of the binaries are very big though, and they're not going to be merging anytime soon. A small fraction are merging now.
Okay.
Yes, there are a lot merging today is sort of what the exciting thing is. And I'd like to assure you that this is actually a fairly conservative estimate. There's a few complicating features that we've had to bear in mind.
Sorry.
Yeah.
Is the what's F here?
Oh, sorry, that's the fraction of the dark matter made of blobs.
And one means 100% dark matter.
Yes.
Okay.
Okay, so the first sort of complication we have to bear in mind is that these binaries form very early in the universe. Yeah.
Just one, just for that formula, like to carry is ym dependence is negative. So the heavier the
Heavier ones, there are fewer merging, but there's also, fewer individual blobs in the universe as they get heavier.
because that's the derivatives from.
Yeah. So these binaries have to survive about 14 billion years intact if we want them to merge today. And there's lots of things that can go wrong. Mainly, they could scatter off of another blob, and either the binary could get pulled apart, or its binary parameters could just get changed in such a way that its merger time is now completely different from what we would have predicted. The biggest effect is blobs forming clusters. If they make up the majority of dark matter, then during matter domination, blobs will tend to form dense self-gravitating clusters. If a binary falls into one of these, it's almost certainly going to be disrupted. So with the estimate I showed you, that's really only accounting for binaries that wouldn't fall into a cluster. The other effect that we have to keep in mind is that binaries are objects with some chunky physical size. The analysis that I've described was designed originally for primordial black holes, and blobs are not necessarily primordial black holes. This means they will almost always collide a little bit early. Generally, it doesn't matter, but once the physical size of the blob becomes comparable to the physical size of their orbit, then they do collide much earlier than expected. But to give you a sense of where this does and doesn't matter, I'd say that for a 10 to the 15 gram blob, as long as its physical radius is less than 10 to the 9 times its Schwarzschild radius, or the radius of a black hole of the same mass, then the physical size won't be a problem. They won't collide significantly earlier. This is a pretty weak mass dependence. This goes as effectively the -1/4 or -1/5 power. And for a sense of scale, the sun's physical radius is about 10 to the 5 or 10 to the 6 times its Schwarzschild radius. So the blobs can get fairly diffuse or fairly puffy before their finite size really begins to mess with the calculation. Yeah.
So on your left side, what's the reason for disruption, like when they fall into the cluster?
Yeah, so it's just there's a much higher rate of scattering. The blobs, other blobs are much more densely packed. So they're more likely to hit something that would change the behavior of the binary.
So it's not a lot more likely they form more binaries.
So it is true that you can form new binaries in clusters, and that's actually something I want to research separately. But that sort of is an entirely separate behavior, so I think that's going to be a separate study that I do.
Of course, in a sense, you cannot just isolate these two labs to look at the gravitational effect alone, right? Then there's collective gravitational potential effect you have to take into account. This is what's a complicated problem. Like
Yeah, and the other complication is, of course, that that binary that forms also has to survive the rest of its life being in a cluster, which I guess is what you're getting at.
The result would be like you just a chunk of data you cannot use. You can only look at very isolated binary.
I mean, so there are simulations that have been done for black hole binaries and clusters like this. And their estimate is that maybe 3 × 10⁻⁴, like of the binaries that fall into clusters survive. So
I
that's,
just mean, how many binaries would be in the cluster? How many binaries would be outside the cluster?
oh, like what fraction don't fall in a
Yeah.
cluster at all? It's like 10⁻³ around there.
Okay.
Yeah. So most are in a cluster, but some wouldn't be in a cluster. And that is enough that we still get a bunch of mergers happening. Yeah. So since we do have a high merger rate, of course, the next question is, what can we actually do with that? Is there some sort of signal we can observe? Well, it's going to depend somewhat on your blobs, but generally speaking, any blob that merges in this way is going to emit gravitational radiation. Whether or not we can see that is going to depend on the strain, which is the amplitude of the signal, and the frequency. Now, the strain is going to increase with the mass of the blob, so heavier ones are easier to see. And it will also increase with the frequency as they spiral in closer and closer to each other. It gets weaker as the blobs are further away, so the luminosity distance between us and the binary signal weakens as they get further away. The other important, number here is the ISCO frequency. So ISCO stands for innermost stable circular orbit. This is the orbit or the frequency where the blobs emit at the highest frequency and with the strongest strain. This is right before they actually collide with each other. And this would be where we generally have the best chance of seeing a signal. Now, blob mergers are going to be a bit different than binary black hole mergers, which a lot of detectors are set up to look for. And they differ in a few ways. So one, during the in-spiral phase over here, which is when the objects are approaching each other, we would expect a higher frequency signal because blobs, well, they can have a variety of masses, but many of them are lower than what we'd expect for astrophysical black holes. Then, because they have finite size, while this might not have reduced their lifetime enough to suppress the merger rate, it will still cause them to merge early in some capacity. And so the merger will happen sooner and at a lower frequency than what would be expected for black holes with the same mass. And then finally, blobs don't necessarily have event horizons. And so this ring down period, which is immediately after the merger, is going to look a bit different, be a bit less suppressed than what one would, again, expect for astrophysical black holes of the same mass. So to give you a sense of what sort of signals are produced, I have here a contour plot where the pink lines are the peak strains and the gray lines are the peak frequencies from the closest blob merger event that you might expect to see given a year of observation time. This is assuming blobs make up 1/100th of the dark matter. The mass is in grams down here, solar mass is up top, and the radius is in terms of the Schwarzschild radius on the left. Now I'm showing you F as 10⁻² because this is the parameter space where you get interesting gravitational signals. But this is also parameter space, which is ruled out by gravitational lensing. So blobs can't be everything in here, but they could be a size, they could be a fraction of it. So there's a lot of fun features on this plot. So I'm going to just walk you through some of them. The first is this grayed out region here. This is where the blob's finite physical size suppresses the merger rate. They're just too big at this point. They're not really merging when they're supposed to. So nothing exciting happening in that part of parameter space. Then you'll notice that there's a knee kind of consistently across the contours here. This is when some of the blobs are beginning to be affected by their finite physical size. Some binaries are merging early, not all of them are. And so the suppression begins to kick in, but hasn't completely destroyed the merger rate just yet. Then there's this dip here into the contours. This is happening because at lighter masses, most of the mergers take place in the galaxy. At higher masses, there are just fewer blobs in the universe in the first place. And so the mergers are taking place mostly outside of the galaxy. And as the typical distance grows significantly when we shift from inside the galaxy to outside of the galaxy, the typical strain we'd expect from the nearest event on an average year, sort of forced down by that jump in the distance to the nearest blob merger. And I'm just going to add a couple of more features to this plot.
Sorry, for that kink structure, due to the finite size effect,
Yeah.
is there two different kind of approximate formulas you use to estimate the rate for the
Yes.
merger? That's why there's a like.
Yeah. Okay, there we go. So yeah, this band right here, this is ruled out by gravitational lensing, even at this fraction of the dark matter. So we can ignore those masses, at least in this plot. Then we have the frequency bands for LIGO and LISA. So I've highlighted them in purple and I guess turquoise. I'm not sure what it's showing up as for you guys. But these are the frequencies that these different gravitational detectors are sensitive to. And then the final part that I am excited about is this region I've highlighted in yellow here. So this is a high frequency gravitational wave region where there's a reasonably high strain. This is interesting because there's been some interest lately in developing high frequency gravitational wave detectors, mostly to look at inflation, gravitational waves from inflation is my understanding. But blobs could also produce reasonably large coherent gravitational wave signals in that frequency range. And there aren't really astrophysical objects with the correct masses and densities to do the same. So this is both an additional motivation for high frequency gravitational wave detectors, and this is a distinct signal that one can look for, and there wouldn't be much competition for what else would be producing such a signal. Now, maybe we can't identify individual gravitational wave events. We can still rely on the stochastic gravitational wave background, which is just a static noise background from all the different gravitational wave, all the different binary blob mergers happening in the present and in the somewhat recent past. What I'm showing here is the blob parameter space, mass and grams down there, here, up there it's in solar masses, radius and short shell radii over on the left. This is where the blob mergers would produce a stochastic gravitational wave signal, which would be observable to LISA. So this would show up above background, above LISA sensitivity in some part of the LISA's frequency band. And this is again, assuming that blobs make up only 1/100th of the dark matter. Now, if we're willing to be a little bit less model independent, a little bit more model dependent, then we can start thinking about electromagnetic signals. And this is relevant, of course, to the lower mass blobs, which are probably too light to produce observable gravitational wave signals. And this is reasonable because if blobs have any sort of coupling to the standard model, then the very violent relativistic collisions that happen with these mergers might produce some sort of electromagnetic something, some sort of signal. And you can make, much more detailed predictions if you have a specific blob model in mind. But even if we don't, there's still statements that you can make about what fraction of the blob's mass can be ultimately converted into electromagnetic particles. And we can even place constraints on that, again, without really knowing much of anything about the blobs. And there's two different ways that we can do this. So one is by looking at distortions to the cosmic microwave background, and the other is by looking at the gamma ray flux. These are both cases where these effects are not very sensitive to the details of the electromagnetic particles produced or many details of what their spectrum looks like, but are still sensitive to electromagnetic anything being radiated. So without knowing much about the blobs, we can still make a statement here. So the first is CMB anisotropy spectrum. Now, shortly after recombination, the free electron fraction in the universe is very low. And the CMB is very sensitive to any new injections of electromagnetic energy at this time. And so there are very strict limits on how much electromagnetic radiation can be produced with energies above about 10 keV. Blob mergers are happening all the time, even at these early times, which means we can use this effect to limit what fraction of the blob's mass can be converted into electromagnetic radiation in these collisions. The other effect that we can look for.
So are you still thinking of a merger event, and during that there's electromagnetic energy exerted on the CMB plasma and then reionizing the thing? Is that the picture?
Effectively, so in the merger, when they collide, there's electromagnetic radiation produced as a result of that collision.
Okay.
Then it can reionize things, it can just excite atoms, and that ends up being a problem ultimately also.
Okay, I forgot the formula, but the lighter it is, quicker it collide or finish the merging.
Heavier things tend to collide faster, but I mean, for the whole mass range I showed you, there's a large number of them merging kind of at all times. They actually do merge at a higher rate at these earlier times than they do today.
Right. I guess my question is that in previous slide, when you mentioned CMB constraint, you mentioned the particles mass greater than 10 keV.
Yes, so that's for the electromagnetic, that's the energy of the electromagnetic particles produced.
Okay. Oh,
So yeah, the collision has to be energetic enough that the electromagnetic particles produced are at least above that energy.
Yeah.
Anything less than that's not really going to cause any problems for the CMB.
And that estimation of number is based on little f being 10 to minus 2 still, or independent of that, because it matters, right? Because
oh yeah, so right now I haven't actually gone ahead and showed you what the constraint is yet. I'll show it in 2 slides, and then I'm assuming f is 1 because we're now in parameter, or this will be relevant to parameter space where there aren't really constraints on blobs generically anymore.
thanks.
Yeah. So, there we go. Okay, so the other effect that one can look for is gamma rays. Now, this is a very high energy effect, and so it's limited to collisions that produce very high energy electromagnetic particles. But if you do produce electromagnetic particles with 36 TeV or more of energy, then these aren't capable of traversing long distances in the universe. They just quickly scatter off of the CMB and produce a gamma ray shower. Now, this is actually a fairly easy thing to look for, and one can just compare the gamma ray shower that would be produced in blob mergers to the actual number of gamma rays we see in the universe and get constraints from that. Together, these 2 effects, oh, and also I'm using the Fermi gamma ray data for diffuse gamma ray backgrounds to get a constraint from this. Now, putting everything together, assuming that blobs make up all of the dark matter now, I can make a statement about what fraction of the blob's mass is allowed to be converted into electromagnetic something in collisions. So this yellow region, which does go all the way up to 1, is ruled out because the blobs produce too many gamma rays when they collide. This is here, this chi is really the fraction of blob mass which becomes electromagnetic particles with at least 10 to the 36 TeV of energy. The turquoise region up there is ruled out for the fraction that become electromagnetic particles with 10 keV of energy. And it's ruled out because they distort the CMB. Yes.
I'm not clear about how you're using these 36 TeV gamma rays. Like Fermi can't see particles of that much energy. So what are you doing?
Oh yeah, no, so those are scattering off of CMB photons, and it ultimately produces a much lower energy gamma ray spectrum.
Oh, so you calculate the evolution of the cascade and everything?
Yeah.
So did you take into account like the infrared background and the scattering of lower energy photons to produce cascades that way? So what I mean, sorry, I'll explain.
Yeah.
So I think your math is right that to exceed the pair production threshold off a CMB photon, you probably need 30 something TeV.
Yeah.
But above 500 or 1000 GeV or something, you can scatter out the infrared background to create cascades. And there's just a lot more power at TeV than 36 TeV. And so I suspect it's a lot, you get a stronger constraint if you do the scattering off the infrared background. Is that something you thought about?
So I mean, this accounts for CMB photons. I know it accounts for inverse Compton scattering with electrons. I'm not actually sure if it includes the infrared background or not. But that's an interesting.
Let's talk about it later.
Yeah, yeah.
Thank you.
So there is one other effect that I'll have to talk about with once we get to blobs at these sort of lower masses. And that's the fact that, I don't know how clear it is on this, but we have a clear region, a region highlighted in light gray and one in darker gray. And as blobs get lighter, it's possible that they could thermalize with the standard model bath. And this can have different effects on the binaries. For this unhighlighted region here, it doesn't matter. If blobs thermalize with the background standard model bath, they will still form binaries and behave in the way that we expect them to. As we get to lower masses though, this starts to become a problem. They might have too much kinetic energy when it's time for them to form binaries and not be able to form them correctly. So in this window here, blobs could be coupled and come up to the temperature of the thermal bath for a time, but do need to decouple early enough that they can redshift away their excess energy before they actually form binary. And then in this region down here, blobs are so light that they actually never can be coupled to the thermal bath, at least not reaching the same temperature as it. If they do, they won't ever be able to redshift away enough energy to form binaries. So these either need to form cold and remain decoupled from the thermal bath, or at least enough that they don't warm up too much.
Sorry, but then another way of interpreting what you said is that, for example, in the intermediate regime, right? If they couple too much to the thermal bath, that means that your constraint does not apply to that scenario. Because they don't form a merger, you can just do like thinking of this binary stuff.
Yeah, so
But that doesn't mean that that scenario is ruled out. I mean, there may be other constraints you need to think about, but.
Oh yeah, certainly.
Okay.
I mean, there are certainly other, well, I mean, they don't form binaries in the same way, so
Right.
that more generally, you have to do a different calculation to estimate the merger rate.
Right.
But yeah, more generally, there are certainly better constraints that you can get with specific models. This is what I'm showing is more a general statement for when you don't know what you're working with.
There's some reason why all these regions are vertical lines.
Yeah. So this gamma ray effect is a present day effect, or this is more binaries merging roughly in the present. The CMB effect is binaries merging at a redshift of 1200. And so the blobs that are merging at these times, or the binaries form at slightly different redshifts, the ones that merge today versus at earlier times. And so they have somewhat different sensitivities to the temperature in the bath. Yeah, but what I'm showing you here, what I'm showing you here today is a tool that I hope is really just the beginning of thinking about these blobs generally and in more detail. There's a lot of work that I'd like to be able to do going forward with them. So one would be making gravitational waveforms for blob mergers. This has already been done for exotic compact objects, so it's very doable. But with this, one could look through gravitational wave data and look for evidence of blob mergers or evidence that we don't see blob mergers happening at the rate we expect them to. Also, there are other ways to get even more mergers than what I described here. And I think you touched on it briefly that you can have blobs forming binaries inside of clusters. You can have blobs which were disrupted and ultimately still manage to collide in the present. So there's sort of a variety of ways to get even more mergers and even bigger signal than what I described here today. Obviously, I'd love to apply this to specific blob models, and I'd also want to think more about charged blobs. So if blobs interact through like a dark U1 or something, then you could have even more mergers happening. They form more quickly, the merger happens much more quickly. The only complication is that they cluster very differently, and that's sort of a separate thing I'd have to think about to address it properly. But yeah, thank you all for listening to me today.
Any questions for? Other questions?
Yeah,
So you said the one model for these to form is have a self-interaction
like
for dark matter to form blobs.
sure, like a strong like self-interaction.
How strong kind of self-interaction? What kind of strong interaction?
Like
Are they contact or long range?
oh no, compact. I'm avoiding sort of the long range self-interactions.
Contact? And
Yeah.
How strong they have to be to form this kind of.
I mean, it's going to depend sort of on
I
your,
think for our stars, right? They formed for some other reason, right? There's some gravitational collapse and so on. But I'm not sure you're imagining such a complicated dark sector or not.
I mean, I'm open to that. I think, yes, this does assume a somewhat complicated dark sector, but I could imagine strong interactions, like similar to what you see in the standard model, where we can build up nuclei. So sort of similar self-interactions to that. Yeah, I'd say like things similar to a lot of what we see in the standard model would certainly work here.
I mean, like if you considered a BBM-like process and you just turned off electromagnetism to prevent Coulomb repulsion, and you made all the intermediate steps that take place during BBN correspond to the formation of stable nuclei as opposed to metastable ones, like for mass numbers 5 and 8, you could make all the matter in our universe iron just during BBN, right? So,
But they don't necessarily form this kind of a compact object, right? So they just float free floating nuclei.
well, it sort of depends. I mean, if you just tweak parameters in your binding energy function by order 1 amounts, you can make very big nuclei. And so I guess they only need like 10 to the 12, let's say, GeV per one of these things, right? Like it doesn't have to.
How big is these things?
So the lightest ones are 10 to the 12 GeV, and yeah, that's sort of the lightest you can get where this still works for them. But yeah, just as you were saying, if you turn off electric repulsion, you can make sort of not quite arbitrarily large, but very, very large nuclei. I believe there are also things, axion quark nuggets, which are made of ordinary standard model stuff for the most part and held together with an axion wall. And those can get exceptionally heavy too. And those are just quark interactions, sort of dense quark nuclei, if you will.
Yeah, I just wanted to make sure we don't see them otherwise. So that this is the leading signal, right? So if you have a complicated model, you may have other things. So this may not be the.
For a given
Yeah.
model, it might not be. I think what's exciting about this is that this is a signal which would be shared by all of the models. This is something that any blob would be able to do. So this is sort of a fairly universal statement you can make about them.
Any model that has a blob.
Any model that has a blob,
Yeah, for this model, how many things are in the blobs? How many of them are all the dark matter in the blobs?
That's a little F, I guess, she took.
Huh?
The fraction of the dark matter.
so yeah, here I'm,
Little f. Yeah, just wondering how likely it is f equals 1.
I mean, this still happens even if F is much less than 1. You actually get rid of some of the suppressions as F gets smaller because they don't form clusters anymore. And so it's actually easier to keep your binaries intact.
Oh, I guess what probably you're asking, given a model, what fraction of them actually form a blob versus like actual elementary particle floating around? Is that your question?
Just some not so larger nuclei. It's like so we actually have these things because we have a lot of complicated things going on.
Yeah.
So,
Also, yeah, in order for the blob to dominate, somehow the nuclear binding energy should peak at some point that only that is preferred to be formed over, say, just say proton, nuclei, and only just floating around, right? Otherwise, we prefer just to stay in the like minimal structure rather than forming a very big.
I'm not sure they wanted to this just literally be a big nuclei. I mean, that seems to me a little. Yeah, you can probably tweak things to make it, but maybe a little bit extreme. Yeah, maybe it's just some astrophysical.
Yeah, unlike in the case of boson star, there is only like fixed point physics, right? They just want to collapse. Of course, there's a repulsion force depending on the gravitational interaction and the self-interaction among the axion. But if you choose the right sign in front of that, then then there's a one direction of phenomena. They just want
Presumably,
to.
this has to be fermions. There's some degeneracy.
Indeed, that's what I'm saying. So
no, I
boson.
mean, I mentioned boson stars as a thing that would be.
Right.
an
So
option
for me,
too.
it's trickier, I guess. You should really rely on some sort of gravitational collapse, and then there's a degeneracy pressure fighting back, and so.
It's really like a neutron star.
Yeah.
You could form one of these maybe in a phase transition, right? Like when people were thinking in the 80s, the QCD phase transition.
Yeah, I'm sure you can do everything. I'm just wondering, how big is how do I think?
Yeah, but like in that case, right, you would have had all this other structure in the standard model, but most of the mass would have been in the form of whatever happened in the regions where bubbles collided. And those would have been dark matter if they'd been stable and if QCD were first order.
But there may be other things too. If you have such a complicated model, we wanted to worry about other things.
So it's true, but if you can get most of the mass inside of those, then the rest of it could just be an epsilon.
And I would say that even if your dark matter doesn't necessarily prefer to be in large blobs, maybe lots of it's in, smaller units, whatever fraction of it does form large blobs, those blobs are still going to do this. So you're still going to have lots of mergers happening of the ones that are heavy enough to form binaries.
I have a silly question. I think on your rate slide, you had a formula that had an exponent of something over 37,
Yes,
which seems like a surprisingly large prime number.
yes,
Do you know where that comes from?
yes, it's an ugly algebra calculation.
Okay.
But okay. I'm thinking about how to.
I mean, it's fine if there isn't a clean answer. If there isn't like
It's
some
not
hidden
really-
37-dimensional space. Like,
It's just all the different dependencies on the mass, because each step has a different mass dependence. So for like the size of the semi-major axis, there's like a mass to there's one over the mass, but then hidden in another term there'll be like a mass to the fourth. And so there's a bunch of different dependencies that slowly coalesce around that horrifying fraction.
Okay, gotcha.
Yeah, just wonder, have you considered like two halos merger with each other? It seems in that scenario, you have a most head-on merger will give us largest signal.
Like if a halo made of a bunch of blobs hit another halo of a
Yeah,
bunch of
like
blobs.
Boolean cluster, those things.
I hadn't thought about that. I know some of like the primordial black hole suppression estimates account for the fact that if one halo eats another halo, then sort of the suppressing effect from the two halos build on each other. But I hadn't thought about halos colliding with each other. The estimate that I showed you pretty much only looks at binaries that aren't in a halo at all. And so tries to avoid having to deal with them entirely.
In other words, like from the bullet cluster, have you seen fireworks? Like if you have electromagnetic thing,
Yeah,
they collide and boom, 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 boom.
so that
Yeah,
would
I
be
see that.
interesting. I think when I think about binaries forming in clusters, that would be a thing I'd have to think about too.
Do they have electromagnetic stuff around it just because of gravity, or they have some other interaction?
I'm for the electromagnetic signals, I'm allowing for the possibility that they have some sort of coupling to the standard model. It doesn't need to necessarily be very strong, just again, because these are very violent collisions of fairly heavy objects. And so you could have some sort of burning process that takes place in the collision. Or maybe the more weakly coupled electromagnetic particles can escape and the dark sector stuff can't escape from the burning. And so you get sort of, again, similar to like what you see in neutron star mergers. Like a fireball, maybe.
Unless there is other more critical question, which I'm happy to wait. I'm still trying to understand 10 keV for CNV. So usually because you're looking at the afterward injection, and therefore you reionizing plasma. Then binding energy 10 eV, right? 13 eV. And then basically you ask, I have this much of stuff which can inject this much of energy. Then overall, what is the fraction of hydrogen atom I can ionize? And you put a bound of that. But then where is this?
Is it ionization, or I thought it was spectral distortion?
I thought it was. I thought it was ionization.
So it's ultimately driving up the free electron fraction. This stuff itself doesn't have to ionize the atoms, though. It can just excite the electrons. And there are still other photons running around that can finish the process off once you've excited the electrons. So yeah, it's not strictly that this has to have enough energy to ionize them. There's a couple of different ways it can ultimately increase the free electron fraction.
This is not distortion, yes.
No,
This is nor reionization that I know.
Yeah, this is apparently happening much earlier, because I thought it was like happening later, and then you're injecting energy to change the observed spectrum, but that's not what's happening.
If
This
you
is
do,
happening.
yeah, if we do on the other hand, well, before CMT couple, you don't get any bound because they anyway normalize.
Yeah,
Right.
yeah. So this is like right after. I mean, this is at Z of 1200. So this is right after that recombination happened.
Yeah, right.
Yeah.
Then it should be reionization. Anyway, okay.
Well, we can continue chatting with Melissa later, but let's thank her once again. Thank you.
Thank you.
I'm waving over here.